Students, today we will discuss equation of motion. We will derive equation of motion from velocity time graph for uniform acceleration. So for uniform acceleration, there is equal change in velocity in equal interval of time. So when we plot a graph between velocity and time, it will come out to be a straight line. Suppose that initially when time is 0, the object is having initial velocity u. So the graph will start from point A and there is uniform acceleration, so it will be a straight line. Now let us draw a parallel line AD and join BC. B is the at B velocity is V. V is the final velocity when time is t. So earlier we have discussed the slope of velocity time graph is equal to acceleration and slope is equal to BD upon AD, and this slope gives acceleration. So acceleration is equal to BD upon AD, or BD is equal to, we know that B at point B velocity is V, at point D velocity is U. BD is equal to BD is equal to BC minus CD, and BC is V, CD is U. So BD is equal to V minus U and AD is equal to T. So acceleration is equal to Vd upon T. Vd is equal to V minus U upon T. This is your acceleration. When we cross multiply it, we will get V minus U equal to AT, or V is equal to U plus AT. This is our first equation of motion, that is velocity time relation. The second is position time relation. We know that area under the curve in velocity time graph gives the displacement or distance. So distance traveled by the object is given by area of OABC. So this was our velocity time graph. This is O, here is A, graph is like this. This is point B, here velocity is V, here velocity is U, here time is T. This is point D, this is point C. So area under the curve or area under the line AB is equal to area of this rectangle OADC, OADC, this area, plus area of triangle ABD, this area, and area of rectangle is OA length into breadth, OA into OC, A into OC, and area of triangle is 1 by 2 base into height, AD into BD. Now OA, OA is equal to U, OC equal to T plus 1 by 2, AD is T and BD is equal to AT, because we know that acceleration in the first equation we have used this formula A equal to BD upon T. Acceleration is equal to slope of the line, that is BD perpendicular upon base. So perpendicular is BD, base is T. So PD is equal to AT. When you put these values, you will get S equal to UT plus half AT square. The third equation is, that is equation position velocity relation. Now in velocity time graph, for uniform acceleration, the graph is like this. This is point A, O, B, C and D. Now the distance will be equal to area under the curve. So distance can also be taken as area of OABD. So distance is equal to area of trapezium OAB and D. This is your D. And area of trapezium is equal to 1 by 2 sum of parallel sides OA and BD. These are parallel sides. This area is equal to 1 by 2, area of trapezium formula is 1 by 2 sum of parallel sides into height. Here height is equal to OD, or this will be equal to AC. This point is D and this point is C, as in the last equation. So this will be your C. So we know that the area under the curve gives the distance. So distance is equal to area of this trapezium. You can apply the area of trapezium formula at here. So area of trapezium is 1 by 2 sum of parallel sides into height. Parallel side is OA and BC. OA BC, sum of parallel side. Height is OC. This will be equal to AD. So substituting the values of OA equal to U, initial velocity, BC equal to V and OC equal to T, and in the first equation, in the velocity time relation, we have derived a equal to v minus u by t, or t equal to v minus u upon a. So here we will put the value of t, v minus u by a. So when we put the value, we will get this. Now we will apply the formula a plus b into a minus b. That is, it becomes v square minus u square, and 2a is multiplied with s, 2as. So this will be our third equation. This is called position velocity relation. The next is uniform circular motion. Know that when the velocity of the object changes, we say that object is accelerating, and the change in velocity could be due to the change in its magnitude or the direction of motion, or both can be changed. When magnitude changes, velocity changes. When direction changes, velocity changes. When both changes, then again velocity changes. So can you give some example where the magnitude do not changes but the velocity changes? We know that velocity can be changed when direction changes without change in magnitude. So the example is circular motion. In circular motion, the magnitude of velocity do not changes, but the direction of motion at every point changes. At this point, direction will be along this direction. At this point, direction will be along this direction. We can find out the direction by drawing a tangent. At this point, direction will be along this direction. So at every point, direction is different, but the magnitude of velocity, that is speed, remain the same, and which is equal to v equal to 2 pi r total distance, 2 pi r upon total time taken. It will not change. So uniform circular motion is an example where the velocity changes due to change in direction, but its magnitude do not change. So it is called uniformly accelerated motion.